So this is a single MOSFET electronic load operating at 350 watts, 30 volts. So this MOSFET, there is a single MOSFET, sandwiched between two heatsink. That is very much necessary because in linear mode, MOSFETs, as we all know, they dissipate a lot of power. So there is two heat sinks, one at the front casing and one at the back, and MOSFET is sandwiched between these two heat sinks to dissipate maximum power. So this is reading temperature actually. Temperature on both the heatsink, that is back side and the front one. So backside temperature is 74 degrees Celsius and the front is 43. The control circuitry, which has a op-amp with negative feedback to keep the VGS voltage stable, and also with very fast response. So we have cooling both the sides. There is one cooling fan here and another one cooling fan here blowing air. So this is a single MOSFET, as I said. If you want more power, you got to put multiple of them in parallel. The MOSFET is a TiVo 264 style package. Wait a minute, I'll show you the MOSFET. So this is the MOSFET IXFB 150p from IXYX, and if you look into the data sheet, you will find this data. Actually, this is really useful data, safe operating area. So this data or this graph says at 150 degree junction temperature and 25 degree case temperature. So this is the case temperature, the temperature on this surface, and this would be the junction temperature. So it says that this is VDS versus ID. Of course, you got to vary the VGS to vary the ID. So at 20 amps, 30 amps, or at 20 volts, 30 volts, 40 volts, you can get 10 amps straight. And of course, as this TC increases, this operating area will shrink and this limit would come down. So we got to figure it out, we got to assume a generous limit below the limit specified by this data sheet, and we got to operate that MOSFET in this region. So if you operate this MOSFET in this region, that means the MOSFET won't blow up. So this is about the MOSFET. And as you go higher voltages, the MOSFET would blow up if you try to pump in more current. It says like this here. So at 100 volts it can go till 10 amps. So that would be 1000 watts, but it's not possible. At 100 volts, 10 amps. In linear region, it would be 1000 watts. So that is possible if you maintain this thing, 25 degrees Celsius. And this condition will be possible for only few seconds. So that's why you see serious cooling in this type of linear loads. So generally, you would see this type of circuit, but this is MOSFET. Op-amp is in open loop. In open loop, the op-amp would have infinite gain, and it would oscillate between saturation and the voltage which is low enough to make these two voltage zero. So that will give you oscillations here which we don't want, which will make MOSFET switch on and off very fast in linear region, and you may destroy the MOSFET. So you got to put some negative feedback like this. So with this negative feedback, you have very stable VGS voltage like this. So this is the VGS voltage across the MOSFET. So what does this negative feedback do? This negative feedback will increase the response time. So with this negative feedback, op-amp wouldn't go all the way up to saturation while controlling this MOSFET. So what does this tell us? This tells us that this op-amp can act fast and control this MOSFET smooth. So you got to have this type of negative feedback. So let us see if we can push to 400 watts. According to datasheet, you can push it to 400 watts. If you monitor this temperature and if you maintain this temperature till just 25 degrees Celsius, it is not possible even with this type of heat sink. You got to go for liquid cooling, coolant cooling. Then it might be helpful. Maybe with a radiator and a coolant, then it might be helpful, but it would increase the hardware. So let us see. So here it is, 400 watts at 30 volts, single MOSFET with ginormous heat sinks, temperatures across, on the heat sink, so this is the maximum which we can go for a single MOSFET.